Well, thank you, one person. Okay, so yesterday we started polar graphing, right? And what we saw was, and I don't know if I mentioned it, and I only thought to say something about it today because someone last period asked me about essentially parent functions. Now, obviously in polar curves, because these things are, circles and other curvy things, we can't call them functions. So what you want to know was, are there parent things, kind of like how there's a parent sine wave and a parent cosine wave? And I said, no, there's not parent equations. In polar curves, you're more likely to talk about parent shapes. So yesterday we talked about circles. Essentially, if you see a sine theta or a cosine theta, you're dealing with a circle. Boom, there it is, okay? We talked about the ones involving cosine having horizontal axis symmetry, how we could reflect the points over the horizontal axis. We talked about ones involving sine having vertical axis symmetry, we can reflect left and right. Cool with that? Okay. So when I was thinking about how to, again, teach this material and what I wanted to do, I was looking at these things here. And these tests for symmetry are, I don't want to say useless, but I want to say they're the kind of thing where they might help a little, but I find them so little help that I don't even like bothering with them. Here's what I will say. If you see a sine theta, then you're dealing with vertical axis symmetry. If you see a cosine theta of any kind, the argument doesn't have to just be theta, then you're dealing horizontal axis symmetry. That's essentially what was going on here, and there's also symmetry with respect to the origin going on here, but you would have to be doing all kinds of tests to even see what's going on, and I'm just not a huge fan of that. And it even says here, the three tests are sufficient to guarantee symmetry, but they're not necessary. That is, if a graph fails a symmetry test, that doesn't mean it doesn't have symmetry. If it passes a symmetry test, then it has to have symmetry. I don't know. Like we already kind of saw it. If you see a sine theta in your function, then you have symmetry with respect to, and it's not even the y-axis. This is not true. It's the vertical axis. You can't call it the y-axis. And if you see your function has a cosine theta in it, then it has symmetry the horizontal axis. You can't say x-axis because the polar coordinate system does not have an x or y-axis. It has a vertical axis and it has a polar axis, which I'm calling the horizontal axis. So yesterday's parent shape was circles. Today's parent shape is rose curves. They're called rose curves because they look like flower petals. That's why they're named that. And we can see a cosine of n theta, a sine of n theta. And rather than filling out this rule for you, I would like for us to develop the rule ourselves. That way we know that we can trust it rather than just going off of, well, Mr. M said so. You guys cool with that? But we really are going to only have time to get through 2 examples. So because of that, I am going to do example 2A, and I'm going to do example 2D. The reason why is because 2A has a cosine in it, 2D has a sine in it. When we were working with graphing trig waves, sine and cosine waves, putting a number in front of theta, what did that do to our period length? If it was, say this was a 2, what did that do to our period length? Divided by 2, right? Yeah. So we know that this number will stretch and shrink our period length. Now, remember when we were solving trig equations, what I was calling the snail shell graphs, the ones where I had to go around a whole bunch of times and find all the intersections? Do you remember when I was saying, what if we replace this argument with something simple, like x or something like that? And we were making not only a substitution in the equation, but also a substitution on the domain. Do you remember how it was stretching the domain as well? You guys remember doing that? Maybe I just need to write it on paper in case you're not remembering what I'm talking about. Grab a piece of scrap. So if I had done this, let's just pretend you didn't have the ability to just see answers or something like that. If I had said, hey, cosine of 3x equals 1/2, and I told you to go from, you don't have to write any of this, and I told you to go from 0 to 2 pi like this, right? What we said we should do is we should make a substitution right here. Instead of saying cosine of 3x, how about we say cosine of theta, where theta is now equal to 3x. But if you make a substitution in the equation, you had to make a substitution on the domain as well. So I need this to say 3x, which forced us to say 3 times, 3 times, 3 times, which adjusted our domain to 6 pi. Now that I've re-shown you, do you guys remember that happening? All right. A similar kind of set of ideas is going to occur here. Also, when we were solving these at the very end, remember when we had all of our thetas equal, numbers, 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 we then said, oh, by the way, theta is 3x. So we were then dividing everything by 3 to solve for x. Those ideas are coming into play here. This is too small for me to work on, so I'm going to go to my note-taking guide, and we will do example 2a here and 2d down below. So we've got 2a here and 2d down there. Example 2a is r equals 2 cosine of 3 theta. We are still going to use the same 8 pretty points, but where they land spoke-wise at what thetas are now adjusted. We still want our cosine of argument to be made up of integer and rational values only. So we're going to draw the 4 triangles for cosine that give us integer and or rational values. So cosine will only have integer results on the quadrantals, and ooh, wow, go home, hypotenuse, you're drunk. Like that. So cosine is x over r. That means, to make sure that we're avoiding square roots, we need our x's to be 1 and negative 1, while all of our r's have a value of 2, like so. So we fill out the size of the reference angle. I'm hoping you're noticing, just like yesterday, that these are 30, 60, 90 triangles, and this angle is across from what would have been the root 3, forcing these to be 60-degree angles. All 4 of them are 60-degree angles. These are the pi over 3 reference triangles. So here's what we need to occur. We need, in order to make this easy for us to do, our argument to have the values that you see here. We need it to be these 8 values. So we need it to be 0 radians, the first pi over 3, then pi over 2, the second pi over 3, then pi, because that's here. Next is 4 pi over 3, 3 pi over 2, and lastly, 5 pi over 3. There is no reason to go to 2 pi because it's coterminal to 0. These are the exact same 8 argument values that we used in yesterday's cosine graph. 0, pi over 3, pi over 2. See, it's the exact same argument values. Is everybody cool with that? Because these are the values that cosine will always give us rational and or integer results for. Yes, Leah? Well, if I used a 1, 1 root 2, then cosine would have had a root 2 in it. The only way to get a rational fraction, there we go, the only way to have only rational numbers is to get the 1/2. And the 1/2 for sine and cosine both come from the 30, 60, 90 triangle. Yep, we're going to stay in 30, 60, 90 land for all sine and cosine graphs. Because now, obviously, cosine will use the pi over 3's, whereas sine uses the pi over 6's, but they both get 1/2 from the 30, 60, 90 triangle. Okay, so this is what we need our thetas to equal. Our 3 thetas to equal, excuse me. So our thetas that we have to actually use require you to divide all of these numbers by 3. Our input values, the thetas that we will use, so multiply all these by 1/3, you get 0. Pi over 9, so we're going to have to estimate where pi over 9 is. And then this one's pi over 6. Luckily, we won't have to estimate that one. That's one of our actual things. This one will be 2 pi over 9. Again, we'll estimate. We'll do our best. And then pi over 3. That one. And by the way, I'm trying to keep these things vertical to each other. I'm trying to keep them in line. Then I have a 4 pi over 9. A pi over 2. Because if you divide this by 3, the 3 that's on top gets canceled. And lastly, the 5 pi over 9. So the blue angles are our actual inputs. But where are the pi over 9's on this picture is the question, right? That's tough. So, especially because it's counting by 12's, which is weird, right? So let's see, let's think. Can we agree that this number right here, pi over 3, this number is 3 of your pi over 9's? Can we agree to that? So imagine you went from here to here, but your job was to cut that zone into thirds. I'm seeing it somewhere around here and here, best estimate. Let me get a little bit closer to that first spoke. Does that look like I cut it into thirds? Okay. All right. We're going to use those as estimates. And I will use a ruler just to, because there's no spoke there, just to pretend there is. So it might be beneficial when you're doing your homework to use a straight edge of some sort. So what we've identified is where approximately our pi over 9's would be. So this would be a single pi over 9. This would be 2 pi over 9. And that makes sense because 2 over 9 is a little bit smaller than 2 over 8. And pi over 4 is, 1/4 is 2 over 8. This one's 3 pi over 9. This one's like 4.5 pi over 9's. So 4 pi over 9 would be, let's see, there's 1, 2, 3, 4 pi over 9 is going to be about there. This number is, if you multiply the top and bottom by 3, you get 6 pi over 9. So this is 6 pi over 9. The 5th pi over 9 is halfway between 4 and 6. So I'm estimating halfway between that number and that number somewhere here-ish. Call that 5 pi over 9. And that's the last one I have to really worry about. You're making a face. You okay with that? Yes, I know they're really small. I'm sorry. Basically what I did was I went with known things. I know that pi over 3 is 3 pi over 9. And I know that 2 pi over 3 is 6 pi over 9. And then I just did my best to cut those zones into thirds. I'm just doing my best. I'm eyeballing it. And you'll do the same thing. You'll do your best. All right, now in the future, like I said, there will be a grid here. So hopefully next year's students, when they're seeing this video, they already have a grid here for them to fill out. But we've got our thetas that we're going to use. And we'll leave a space for a little bit of work. And the r associated with that theta, that's only going to be 4 of the coordinates. So the other 4 coordinates will happen here, like so. These are our thetas. The first 4 will go here. The next 4, for space purposes, will go down here. And we are ready to go to work. What we've done is we have strategically chosen thetas to force cosine of our argument to be the integer and or rational values that cosine can give. So we start at 0. 3 times 0 is 0. See? So if we use this blue theta, we're actually evaluating cosine at this black angle. We're actually evaluating cosine at 0, which is here. Cosine of 0 is 1. So this gives me 2 times 1, which is 2. We begin at the coordinate 2, 0, which will be right there. I think it's important to know where you start. So I'm going to put a marker of some sort, letting me know that was where I began. Now pi over 9, realize that when we input pi over 9, and actually let me show it one time down below. Let me show you me inputting pi over 9 so you can see exactly what I'm talking about. 2 cosine of 3 times pi over 9. But you see 3 times pi over 9, 3 pi over 9 reduces to pi over 3. And now if we come back up here, what I was saying was, when we input this, we're forcing our, I was going to say function, we're forcing our equation to evaluate cosine at this angle. That's the idea. And that is right here. So we're going to force this to always evaluate at somewhere nice. Cosine at this angle, so pi over 9 goes in, we're doing cosine of pi over 3, is 1/2. It gets me 2 times 1/2, or a value of 1. So go to the pi over 9 mark that you made. With something straight, try to connect it to the origin. And then go out to, what was the radius? 1. The first radius. Like that. And you're just doing your best. If the dot is fat enough, it's kind of hard to argue with, isn't it? Now go to pi over 6. If you input pi over 6, you're evaluating cosine at 3 pi over 2. Cosine, no, pi over 2. I saw the 3. If you input pi over 6, you're evaluating cosine at pi over 2. Cosine at pi over 2 is 0. So this is 2 times 0, or 0. That, ladies and gentlemen, is the pole. So what did we do? We started here, and we arched in a counterclockwise motion to the pole. Like that. Good? And it should make sense that it went counterclockwise motion because, well, you know, our angles go counterclockwise, don't they? Now let's get 2 pi over 9 on here. If you input 2 pi over 9, it's equivalent to evaluating cosine at 2 pi over 3. That's here. Cosine here is negative 1/2. So I have 2 times negative 1/2, which gets me negative 1. So I'm going to go to my 2 pi over 9 mark. I know it's an estimate, but we're going to go to that 2 pi over 9 mark. We're going to connect it to the pole / origin. Realize, though, that the radius is negative, which means I can't stay over here. I have to reflect away from here to over here. That means we continued in a counterclockwise motion and went to there. Remember, this is cosine. Whatever happens on one side of the horizontal axis happens on the other side of the horizontal axis. Let's keep going. Pi over 3 is going to force our equation to evaluate cosine at pi. Cosine at pi is right here. That's negative 1. So I have 2 times negative 1, which is negative 2. Now the pi over 3 spoke is there. And because the radius is negative, I do have to reflect to the other side onto the second ring. Slowly connecting the dots as we go, but you notice we're still moving in a counterclockwise fashion. 4 pi over 9 evaluates cosine at 4 pi over 3. Here's 4 pi over 3. Cosine here has a value of negative 1/2, right? Yeah, negative 1/2. So we get 2 times negative 1/2, which is equal to negative 1. So you go to your 4 pi over 9 estimation, connect it to the pole, but because the radius was negative, reflect to the other side, we're about here-ish, because it's on the first ring. So what did we do? We did this, still moving in a counterclockwise fashion. Now pi over 2. Pi over 2 forces cosine to evaluate at 3 pi over 2. Cosine of 3 pi over 2 is 0. It put us back on the pole. That sounds horrible. We're back on the pole, everybody. Gotta make that money. And the last, quote unquote, last one, 5 pi over 9, okay? 5 pi over 9 forces my cosine to evaluate at 5 pi over 3. That evaluates this triangle. So I'll have a positive 1/2. I have 2 times 1/2, and that gets me a value of 1. So that 5 pi over 9 estimation at the first ring, I got to here. Huh. Well, that's a little strange because that image didn't close itself, did it? You know why it didn't close itself? We only went out to 2 pi. In order to see the whole image, we would need to go out to 6 pi. Now, I don't know about you, but I'm not trying to do that many coordinates. Luckily, we have knowledge of the symmetry that a cosine graph in polar coordinates should have. It should be symmetric over the horizontal axis, which means this arch has a reflection to there-ish, and this point already reflected there. This point would reflect to there-ish, and this point reflects to, was that the second ring? There. So here's the whole image. And to be honest with you, it actually goes around this 2 times. It goes around twice. So how much of the graph did I actually see when I stopped at 5 pi over 9? I saw exactly 1/3 of it because it traces this image twice. So I saw exactly 1/3 of the graph. Would you be able to tell that the second time around was just laying on top of the original? No. You would have had to have plotted all the points from 0 to 6 pi to make that work out. Man, that would have been painful. Okay? That's a ton of points. But trust me when I say, it went around this twice, just like yesterday's circles went around twice. Cool? Now, I want to show you the path it traces. So this is our graph. I'm always ready to rock and roll. I'm looking at my window, and I change my step to slow, and I'm going to let it go through the 2 pi's. Now watch the path it goes. Funny. You're funny. 2. There. Now I don't know if you can see it, but it went around a second time. Some of the pixels got fatter. I could see it because I'm really close to the calculator. I don't know if the camera picked it up well enough, but it did go around a second time. And the proof of that is I could change this to 1 pi and it'll still make the whole shape. But it's done right there. So you didn't see it go around a second time, but it definitely does. Also notice that the motion is always counterclockwise. Started here and went in a counterclockwise motion, continued going counterclockwise, continued going counterclockwise, and it did go around twice. Isn't that neat? So now let's go back to the actual notes. for 2a. And let's talk about what we saw. We saw symmetry over the horizontal axis. Yes, Nolan?
If you change the equation we just did to 2 theta, would it have 2 flower petals?
So the question is, if I changed this number in front of theta, which is actually what we're trying to discover here, we're going to do that in this example. So you will see. You will see how, and that's literally what we're trying to do right now, is figure out what happens to the flower itself and the number of petals as n increases or decreases. That's the real question, right? Okay, so symmetry, what graph was this blue? Yeah, it was blue. So symmetry, we said over horizontal axis, and that makes sense because it's a cosine graph. Now n for this one was 3, which is an odd number. Clearly something's going on with even and odd. I count 3 flower petals. I don't feel like trying to draw it on here again. We've got the companion, right? I just don't feel like drawing it on here again. Let's see what happens if I did this one. Actually, you know what? I'll hold off on it. We'll do that at the end of the video, if I have time. Let us go to 2d now, 4 sine of 2 theta. Now remember, if we wanted to see the entire graph, we would have to stretch the domain from 0 to 2 pi, doubled. We'd have to go out 0 to 4 pi to see everything. Once again, that's too much work in my mind. I would rather trust symmetries. This is a sine graph, and sine polar graphs should have vertical axis symmetry. That's what I expect. So I expect to be able to see enough of this thing if I just go 0 to 2 pi without going all the way out to 4 pi to complete the whole graph. Like we mentioned earlier, sine and cosine are both going to get their 1/2 values from the 30, 60, 90 triangle, but they're going to get it at different angles. Cosine was getting its 1/2s at the 60-degree angles, the pi over 3s. Sine will get its 1/2s from the 30-degree reference angles, the pi over 6s. So we need 2 theta, because that's now our argument, to be equal to the 8 special things we see here. 0, pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2, 11 pi over 6. Oh, and I don't need to do 2 pi. Is that 8? 1, 2, 3, 4, 5, 6, 7. Okay, there's all 8 of them. Great. So to get theta alone, just like we did for this one, when we were solving these kinds of things at the very end, you know how to have to divide? We have to divide by 1/2. No, we have to divide by 2 right now, which is the same as multiplying by 1/2. Good news, everybody. These denominators will be 12ths. And this is cut into 12ths. So we won't have to estimate any spokes this time. Here's the thetas that we will use. We will use 1/2 of 0, 1/2 of pi over 6, so pi over 12, 1/2 of pi over 2, pi over 4, 1/2 of 5 pi over 6, 5 pi over 12, 1/2 of pi, I think you see what's happening, 7 pi over 12, 3 pi over 4, and 11 pi over 12. There. And every one of those is a spoke. We don't have to estimate anything. Yay! That makes life good. No estimations necessary. There's a reason why I skipped over 2b. Because they would have to all be like 15ths or something like that. Yeah, it would have been ugly. Alrighty, let's get it filled out. We've got the thetas, leave a little space, and then r, theta, leave a little space, then r. The first 4 thetas, 0, pi over 12, pi over 4, and 5 pi over 12. Come on down. Pi over 2, 7 pi over 12, 3 pi over 4, and 11 pi over 12. Remember what we're doing. We're forcing this equation to evaluate at these places, which are these places. So when we use theta is 0, we're evaluating at sine of 0. Sine of 0 is 0. This gives me 4 times 0. Oh, I'm starting at 0, 0. Starting on the pole. See where we're going. At pi over 12, which will be our first spoke, we're evaluating sine at pi over 6. So 1/2. We have 4 times 1/2, or 2. So at pi over 12, second ring. I'm hoping you will notice that we have just swept out in a counterclockwise motion. Should not be surprised by that. At pi over 4, we're evaluating sine at pi over 2. Sine of pi over 2 is 1. So I have 4 times 1, or 4. Sheesh. So go to pi over 4, and you're on the 4th spoke, or 4th ring. 1, 2, 3, 4, right there. So it's continued counterclockwise. 5 pi over 12 forces sine to evaluate at 5 pi over 6. That evaluates here. 1/2 again. Yes. Okay. Make sure you just watch the video. Then we're at 5 pi over 12, 2 comma 5 pi over 12. This is the 1, 2, 3, 4, 5th. Here's the 5th pi over 12. It's right here. And we're on the second ring, right there. So far we've done this. Where do you think we're headed next? Nobody said anything. Okay, well, either you have no idea or you're afraid to talk. I'm not sure. Let's go with pi over 2. That forces sine to evaluate at pi. Sine of pi is 0, because it's here. There's no y value. So we have 4 times 0, or 0. Oh, pi over 2, comma 0. Well, I said it backwards. 0, comma pi over 2. We're back at the pole. So here is what the graph did. It swept out and around and came back, like that. Now sine has vertical axis symmetry. So this loop that I just made will have to exist over here. But we're not there yet. Let's keep on keeping on. The 7 pi over 12 forces my equation to evaluate sine at 7 pi over 6, which is here. So I now have a negative sine value. 4 times negative 1/2. Or negative 2. Okay, so I'm not very good at the seeing where it reflects over to. So I'm using my straight edge to show me that. That is the 7 pi over 12. Negative radius puts me over here. So I've now done this. When I came back through the pole, I did that. 3 pi over 4 forces sine to evaluate at 3 pi over 2. Sine there is negative 1. 3 pi over 4 negative radius reflects to there, and it's on the 4th ring. 1, 2, 3, 4. So we are still moving in a counterclockwise motion. And then the 11 pi over 12 forces my sine to evaluate at 11 pi over 6. Evaluate here, negative 1/2. 4 times negative 1/2 gets me negative 2. 11 pi over 12 is this one right here, because this is 12 pi over 12. So we go here, and we have a negative radius. So again, reflect across the other side onto the second ring right there. And here's what happened. Oops, I missed my dot. Grug. There we go. Now guess what would have happened? If I had gone to 2 pi, you know 2 pi is coterminal 0, right? If 2 pi is coterminal 0, everybody's cool with that? That means after here, I would have been right back here again. Like that. It would have done that. But remember, this stretched our domain. Instead of going 0 to 2 pi, this would have made us go to 4 pi to see the entire shape. Rather than do that, I would like to use symmetry ideas and say, because this is a sine polar graph, it has vertical axis symmetry. So every one of these points that I have on the right side of the vertical axis, I'll reflect over to the left side of the vertical axis. That means I've got a point here. That's this point. This one is at a pi over 4 on this ring, so it's right there. This one's on the first spoke up, second ring. So I have this shape here. This one is 1 spoke to the right, so go 1 spoke to the left. This one's at a pi over 4 of some sort on the fourth ring, so that's here. And this one is 1 spoke down, second ring, 1 spoke down, second ring, and you have this shape. But I would like you to see its path. Here's its path. You start here and move counterclockwise. Counterclockwise, counterclockwise, counterclockwise. The motion was always counterclockwise, even as we went around our petals. And just to prove a point, let's get on here. This was 4 sine of 2 theta, and it should go slow enough for you to track it. Oh, of course, my window's not large enough. But you see what happened? Zoom square. That didn't help at all. How was that square? It's offset. That's stupid. Well, you get the idea, right? See it? Pretty neat, huh? So let's talk about some things. That went to 2 pi. What happens if I only went to pi? I saw exactly half the shape. So in order to see this whole thing's, the entire shape, you needed to go all the way out to 2 pi. So why doesn't that happen when the number in front of theta was odd is the question. Well, yesterday we worked with sine and cosine who had an odd number in front of theta, didn't we? You used to have a 1 in front of them. And I told you yesterday that we go around those things twice. This image had an odd number in front of theta. It went around it twice. This one had an even number in front of theta. It only went around this image exactly 1 time if we had gone all the way out to the full domain like we should have. So let's go back to the actual notes then. This one, because of sine, had symmetry over the vertical axis. This time n was 2, which happens to be an even number. But I saw, get in there, 4 petals. Then let's come back. And rather than me just telling you this truth, you could probably tell me. If n is odd, how many petals do you think we'll get? N petals. And the reason why is because you traced the image twice. Or cover image, I don't want to say that. Cover the image twice, trace the image twice. What would you say? Trace the path twice. Go around the same image twice. I'm going to say twice around. How about that? Twice around. But if n is even, how many petals do you expect? Not over 2, times 2. Okay? 2n. So we had a number in front. We had a 2 in front. And we got 4 petals. And it goes once around. Now to prove this point, this is a sine graph. And we expect our sine graphs to be symmetric over the vertical axis. In here is 5, which is an odd number. How many petals are we expecting this to have? 5 petals. I'm not graphing this by hand. We're going to do it on the calculator to prove the point. I could just put it on a Desmos, but I'm not going to. What is this? 3 sine 5 theta? Oops. 3 sine 5 theta. Now let's see if we get 5 petals. And what is sine of 0 again? Zero. That means this graph had better start at the pole. It did. It started at the pole, and it moved in a counterclockwise motion the entire time. Kind of cool, huh? Then this one. Because it says cosine, we would expect this to be symmetric over the horizontal axis. Here, n is 4, which is an even number. So how many petals would we expect it to have? 8 of them. Sheesh. What happened? How much of the graph did we just see? Exactly half of the graph. Reflect it over the horizontal axis. And these 3 double. Now you have 6. That completes 7. That completes 8. I only had it going from 0 to pi. So let's fix that. 1. There we go. Keep it going. Oh yeah. Ta-da. Beautiful. How about that? So we've now successfully mastered, I'm going to say, mastered circles and rose curves. Yeah? Thanks, nerds.